Hi, I'm Bob. Welcome back to 5-Minute Econometrics, a program focusing fundamental econometric concepts and estimation methods. In the previous topic, we discussed how to use dummy variables to describe the difference in the outcome variable between two groups of people. Today, we will explore the cases of interactions between one continuous variable and one dummy variable, and the interactions between two dummy variables. We can use one single dummy variable in the model. If we draw a picture of the OLS fitting line, we find that the coefficient for the dummy variable represents a shift in the intercept. For example, here is the regression of wage on education and gender. We can write down equations for male workers and female workers. Then we draw the fitting lines for them. The coefficient of the dummy variable female, beta 1, is the intercept shift from male workers to female workers. On the other hand, we know that the slopes of the fitting lines are the marginal effect of education on wages, that is, the return to education. The two fitting lines for men and women are parallel, meaning that we assume the return to education is identical for males and females. However, the returns to education may differ between male and female workers. To allow for different slopes, we can add an interaction term between education and female to the model. We write down the equations for men and women. We find that the slope of the fitting line for men is beta 2 hat, while the slope of the fitting line for women is beta 2 hat plus beta 3 hat. The slopes of the fitting lines are the returns to education. We allow the returns to education differ between male and female workers. This graph is for the case when beta 1 hat is negative and beta 3 hat is positive. We can figure out other cases, such as the one where both beta 1 hat and beta 3 hat are negative. From this example, we understand that if we include an interaction between a continuous variable and a dummy variable in the model, the marginal effect of the continuous variable on the outcome variable can differ across the two groups defined by the dummy variable. Here, the marginal effect of education on wages can differ by gender. Let us estimate the model using the OLS method with a sample of 526 US workers. We want to find out whether the return to education is identical for male and female workers. The null hypothesis is that the parameter beta 3 equals 0. The alternative hypothesis is that it is not 0. Stata reports the estimates and the statistics in its results window. We can write down the estimated equation in standard form. The standard errors are in the parentheses. The estimated return to education for men is 0.077 or 7.7%. The estimate for the interaction term is economically negligible and statistically insignificant, as its t-statistic is nearly 0 and the p-value is close to 1. we could not reject the null hypothesis at any conventional significance level. There is no evidence against the hypothesis that the return to education is the same for men and women. The above case involves an interaction term between a continuous variable and a dummy variable. Next, we will focus on the interaction between two dummy variables. It is called difference in differences in econometric analysis. The elements of the difference in differences measure are two dummy variables, one indicating the treated group and the control group, and the other describing the time before and after the treatment. The interaction term between the two dummy variables captures the causal effects of the treatment. Here is an example. In 1980, Kentucky passed a law that makes it less costly for injured high-income workers to remain on workers' compensation, but did not affect injured low-income workers. The dummy variable treated equals 1 for high-income workers and 0 for low-income workers. Another dummy variable after equals 1 after the law was enforced and 0 before the law was implemented. A simple regression model includes both dummy variables and their interaction term as the explanatory variables. The outcome variable is the length of time that an injured worker received workers' compensation. The treatment here is the law implementation, and the treated group is the high-income workers because their choices were affected by the law. The control group is the low-income workers because the law did not impact them. The table shows the expected outcome in 4 different situations. Please refer to topic 34 for detailed information about the difference in differences measure and how to read this table. I have attached the link to that video. The difference in differences is beta 3, which is the ceteris paribus change in the outcome due to the treatment. In Stata, we regress the log of the length of compensation time on the two dummy variables and their interaction term for the workers in Kentucky. The OLS estimate for the interaction term is 0.191, indicating that the law increases the duration of compensation by about 19%. The t-statistic is 2.78 and its p-value is 0.005. The interaction is statistically significant at the 1% level. Notice that there is an upward trend in the control group. The difference in differences measure considers the trend and assumes the treated group has the same trend. We can visualize the difference in differences effects in a graph. After removing the trend, we obtain the ceteris paribus effects of the policy. Today, we discussed the interaction terms between one continuous variable and one dummy variable. Using the interaction allows the marginal effect of the continuous variable on the outcome variable to differ across the two groups defined by the dummy variable. We can also use the interactions between two dummy variables to obtain the difference in differences effect of a policy or program. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.